let's go through some examples of circular motion. When something moves in a circle, there are actually only two cases. You either have something moving in a horizontal circle or something moving in a vertical circle. Okay, so the first example we go through today is for motion in a horizontal circle. So we first talk about a mass that is tied to a string. Okay, now we consider a mass that is tied to the end of string that is swung in a horizontal circle with constant speed. So this is a top view where a person is actually holding a string attached to a mass and then is trying to swing it, say, in this direction in a circle. So since this mass is moving in a circle, we know that there must be centripetal force that caused the object to move in a circle in the first place. If something moves in a circle, there is centripetal acceleration, correct? But at the same time, there must be centripetal force that causes it. Okay, so since this object is moving in a circle, there must be centripetal force here that caused the object to move in a circle. But what actually provided you the centripetal force? In the case that is described here, is actually the tension in your string that provided you with your centripetal force to make the ball follow a circular path. Okay, the tension in the string here was actually the thing that provided you your centripetal force. Okay, now if you keep swinging your mass in a circle, if you swing it too fast, you can imagine that eventually the string will snap. Okay, now in the case where the string suddenly snaps under tension, what happens then would be that the ball won't continue to move in a circle. Instead, it will continue to move in a straight line tangent to the circle at the point where it snaps. So if, say, the object was originally at this position, and then you swing it too fast or too hard, and then all the way to here, your string suddenly snaps, the mass here won't continue to move in a circle. Instead, you just move off tangent to the point where it snaps. Okay, that is what this statement here is trying to tell you. Okay, just know that whenever something breaks, that thing cannot move in a circle anymore. You just move in a straight line tangent. All right. Okay, now if you want to analyze the motion of this object that's moving in a circle right now, looking at it from the top view won't really give us much information. It will be much more useful to look at it from the side. Okay, let's just say right now we look at the circle, the object moving in a circle from the side. When we look at the object that is moving in a circle from the side, there are two different directions to consider. We need to consider the vertical direction as well as the horizontal direction. Just like your kinematics last time, when you have something that moves in a parabolic motion, like your projectile motion, you always consider the horizontal motion and vertical motion, right? So it's something similar here for circular motion. You have to consider the vertical and horizontal motion. Now, when you are swinging the stone so that it moves in a circle, it was mentioned just now earlier that your stone was moving in a horizontal circle. So when your object was moving in a horizontal circle, your stone actually did not move up or down during the motion. Its vertical position was actually maintained. So since it didn't move up or down, its vertical position remains the same, there's actually no vertical resultant force. So if I were to analyze the forces later, you will notice that there's no vertical force, no resultant vertical force, okay? But what if I consider the forces horizontally? Now, if I consider the forces horizontally later, you will find out that there's a resultant force that actually allows the stone to move in a circle, okay? So why am I saying these first two statements? You look at the side view of your stone tied to a mass. Just now it was mentioned that your stone is tied to a string. The string would exert a tension T onto your stone. Okay. Now this tension T can be resolved into two perpendicular components. You can resolve it in the horizontal direction like this, as well as the vertical direction like this. Okay, now you'll notice that this one forms a zigzag. So if I have an angle theta here, there must be an angle theta here also. All right. So now from here, I can actually work out an expression for the tension components. The horizontal component, the blue arrow here, would actually be T sine theta. Whereas the vertical component, the green arrow here, because it's adjacent to my arrow, sorry, it's adjacent to my angle, it will actually be T cos theta. Now, the blue arrow, why do I say is sine? Is mainly because if I were to shift it to this side to complete the triangle, you will notice that this is actually opposite to your angle, so it's sine. All right. But some people don't like this kind of reasoning. The easiest they do, the easiest thing they'll do is that they just see which component is adjacent to the angle first. So they see this component is adjacent to the angle is cos, the other component must therefore be sine. That's how they remember it. Okay, so it's up to you. But at the very least, just make sure you get the tension components correct. Okay, the vertical component is T cos theta. The horizontal component is T sine theta. Okay, now just now I mentioned to you that there are no resultant vertical force because the object did not move up and down. What's happening here is that your mass was moving in a horizontal circle like this. Okay, during the time that is moving in a horizontal circle, the stone never move up and down. So no motion up and down, vertical position maintained, no resultant vertical force. This would mean then T cos theta must be balancing the weight. So you have T cos theta equals to mg. This is the first relation that you can see from here. Okay. But then after that, when you move on to the horizontal motion part, you will notice that T sine theta is the only force acting here. It doesn't seem to be balancing anything else. So this one here is actually your resultant force, which is actually acting as your centripetal force. Okay, this T sine theta is actually the force that is acting as your centripetal force right now to allow your mass to move in a circle. You see, this one is the center of your circle, isn't it? COC. This force is pointing towards the center of the circle. It's actually acting as your centripetal force right now to allow you to move in a circle. So if I use equation Fc equals to mv squared over r, my Fc is actually T sine theta. Then it's equals to mv squared over r. So this is the second relation that you know. Now, you want to simplify these relations that you found out. One of the things you can do is you just take equation 2 divided by equation 1. You take equation 2 divided by equation 1, the t's will cancel. Sine theta divided by cos theta will give you tangent theta. And then mv squared over r divided by mg will give you v squared over rg. All right. So this one can be used to represent the object moving in a circle right now. Okay. Now you don't need to remember this equation. This is not required in your syllabus, but what you need to know is how you analyze the diagram to work out some sort of relation. It's more important for you to be able to analyze the situation vertically and horizontally in order to derive some sort of relation. That is the more important thing here. Don't memorize this final equation here because this is not the aim of the syllabus. The aim of the syllabus is to ensure that you at least know how to analyze any given circular motion questions. Okay, so this is one thing to note. Okay, another thing I should probably mention to you is this. You guys probably would have tried your hand before at tying a mass onto a string and then trying to swing it in a horizontal circle. one of the things that you might have noticed was that if you swing your mass faster, the string with the mass tends to go higher. Meaning to say, if let's just say my speed increases, the speed with which I swing the mass increases, my string would actually go higher and higher and higher, right? If my speed increases. So one thing to note here is that no matter how fast you swing your mass that's tied to the string will never ever be perfectly horizontal. Because what will happen is that when theta is 90 degrees, like the one that you're seeing right over here, you will notice that nothing will actually be balancing your weight. Just now the mass is tied to the string. The mass has its own weight W, and then you also have tension T inside the string, right? So if you consider the case where your string is perfectly horizontal like this, there's actually no force that is balancing your weight. So it won't maintain in a horizontal position, okay? There's no component of tension that is actually balancing the weight now. Just now previously, there's actually a component of tension that is actually balancing the weight. That was T cos theta. That allowed your mass to remain vertical, that allow your mass to remain in the same vertical position. But if you're considering the case where the string is perfectly horizontal, it just cannot happen because there's no component of tension balancing the weight. Okay, so the mass will actually just move down instead of maintaining the position vertically. All right. All right, so if you move back to the notes under page 4, there are also other different cases where something moves in a horizontal circle. The first example we did was for a mass that is being swung in a horizontal circle when it's tied to a string. Now, there are also other things that can move in a horizontal circle. For example, when an aircraft is flying. Now, when an aircraft is flying, say we have an aircraft that looks like this right now. Let's just say that this is the top view of the aircraft. And then say your aircraft wants to go to this spot here. If your aircraft was originally flying in this direction, in order for you to move to this spot, it will have to turn to move to this position, right? So usually when it turns, it may turn like this. Okay, it curves like this. So when it tends to curve or turn like this one here is actually part of a circle. Okay, the motion is part of a circle. This motion is part of a circle. It doesn't move a full circle, it moves part of a circle. All right, but for all manners and purposes, we still consider this as circular motion for the green highlighted portion. So since this green highlighted portion is moving in a circle, we also know that when it tries to turn to go to this spot here, it therefore must have centripetal force that's directed towards the center of the circle that allows it to move in a circle in the first place. Okay, now when an aircraft is trying to turn in the air, when it's trying to make a circle in the air, one thing to note is that the aircraft must actually bank, okay, in order to move in a circle. Now, what is banking of an aircraft? Banking just simply means something like this. You are actually rolling to one side. The aircraft rolls to one side. It tilts to one side now. In other words, what do I mean by that is, let's just say if I look at the aircraft from here, the front view, I tell you that, say maybe this one is the front view of the aircraft before banking, it will generally look like this, where your wings are straight. Okay, notice that here your wings are straight. But when it starts to bank during during the part where it wants to move in a circle, it will now look like this. Your wings are tilted towards one side. It's actually rolling to one side. So this is the same aircraft, but banking. Okay, this is the front view, but during banking. All right. So you notice that your wings are tilted right now, and they are at a certain angle. Now, it is important to note that when your aircraft is flying, your wings will generate lift. Okay. The reason why your aircraft can fly is because the wings are generating lift to lift your aircraft up. And your lift is always perpendicular to your wingspan. So for the aircraft that is actually flying, you have the weight W acting downwards, but you also have the lift force that is generated by the wings. It will always be perpendicular to your wings. The lift force is always perpendicular to the wingspan. Okay, it's always perpendicular to your wing. All right. So if you're talking about the aircraft right now, if you consider the forces for the weight and the lift force, if your aircraft is trying to move in a circle, let's just say I tell you that the center of my circle is right over here. If you just look at the aircraft as it is right now, there is only vertical forces. There are no forces pointing towards the center of the circle to allow me to move in a circle. Just like I mentioned to you, if you have something that wants to move in a circle, you need to have centripetal acceleration, you need to have centripetal force. Centripetal force must come from some other existing force in the first place. So if you consider the case where the aircraft does not bank, the wings are perfectly horizontal like the ones that you're seeing at the front view, there are actually no forces pointing towards the center of the circle. No forces pointing towards the center of the circle means there is no centripetal force. So your aircraft cannot move in a circle in the first place. Okay, that's what the first two statements here are actually trying to tell you. A flying plane makes a turn in the air, it must bank to do so. If the plane does not bank at all when theta is 0 degrees, there's actually nothing that provides you your centripetal force. So your aircraft must bank in order to move in a circle. Why do we say this? Is because just now I mentioned to you that your lift will always be perpendicular to your wings, right? So if your lift is perpendicular to your wings, the moment your aircraft banks, your lift force can actually be resolved into two perpendicular components. A vertical component like this one, and a horizontal component like this one. Okay, so when it banks, it will tend to make a certain angle. Let's just say we consider the angle that it makes to the vertical. So the blue colored arrow, the vertical lift force, will be actually L cos theta because it's adjacent to your angle theta. The other component would therefore be L sine theta. So if I'm trying to move in a circle and I tell you that this is the center of my circle, I actually now have something that acts as my centripetal force. In my case, it's actually L sine theta. L sine theta is actually helping me to provide the centripetal force so that I can move in a circle. All right, that's the reason why your aircraft needs to bank right now so that you can have a force that acts as your centripetal force. If you don't bank, there's no centripetal force. So in your case, your aircraft must bank in the first place. Okay. Now, same thing as before, for the aircraft, we want to analyze the horizontal and vertical motion. Now, ideally, when your aircraft is banking, the aircraft will not fall down from the sky and it won't suddenly go up, isn't it? It by right ideally should maintain its vertical position, just like the mast tied to the string just now. So in the case where we try to consider the forces vertically, we can actually say that the weight W of the aircraft will be balanced by L cos theta. That's why L cos theta equals to mg here. This diagram here is actually this diagram here. Okay, it's the same thing, right? So vertically, no vertical motion, L cos theta will be equals to mg. But then now when we consider the forces horizontally, we know that this L sine theta is actually acting as my centripetal force. So L sine theta is actually mv squared over R. All right. Now I want to simplify this relation. I can take equation 2 divided by equation 1 because I want to get rid of sine and cos. I want to make them the single function. So equation 2 divided by equation 1, L will cancel. Sine theta, cos theta will give me tangent theta. Mv squared over R over mg will give me v squared over rg. So this relation here applies to the banking aircraft right now. Okay, so same thing as before. No need to remember this, but please be aware how to analyze the forces and how to derive some other resulting expression. This is the more important one. Okay, so this is banking of an aircraft. And then another thing I should probably mention to you is this. Now, when an aircraft is banking, your aircraft actually needs to increase its speed. So that its lift force L also increases. Now, before your aircraft was banking, before you made the aircraft bank, the lift force was equal opposite to W so that the plane does not fall. Meaning to say, if you look at this diagram right now, if I tell you that my weight was 1,000 Newton, the lift force must also be 1,000 Newton in order for your aircraft not to fall out from the sky. But now you consider this, if your aircraft banks, but without increasing its speed in the first place, look at what happens to L cos theta. Say my weight now remains the same as 1,000 Newton, but my angle now is, say, for the sake of discussion, is 60 degrees. Let me just erase this. Let's just say that my angle theta that I have is 60 degrees and my lift force remains at 1,000 Newton as before. My lift force remains at 1,000 Newton. So what happens to L cos theta? L cos theta would now be 1,000 cos 60. You actually have 500 Newton only. Okay, so previously, just now, you have L balancing the weight. They are equal opposite, so your aircraft did not fall off from the sky. But now, L cos theta is supposed to be balancing the weight, but the values are not equal. L cos theta is actually less than the weight. So therefore, the plane will fall. Okay, so here I actually already wrote it here. If the plane banks without increasing its speed, L cos theta is now less than weight W, so the plane will drop. Okay, but it's still able to move in a circle because you still have the L sine theta here acting as your centripetal force. It's moving in a circle, but it's dropping off from the sky, which is not something you want. You want to maintain your position in the sky while moving in the circle, right? So one way of doing that was to increase its speed. Okay, so just now I mentioned to you that lift force is always perpendicular to the wingspan. Another thing to note here is also this. The faster the aircraft moves, the larger the lift force generated. Okay, so that's the reason why we have to increase our speed in the first place, so that our lift force increases. So if we fly faster, we have a larger lift force. So by having a larger lift force, it could come to a case where now L cos theta is larger so that it can balance W. So let's just say, for example, if I say that my aircraft flies faster right now, if it flies faster, it could be that my lift force is now 2000 Newton if it was flying faster. So now, if it is now 2000 Newton at the same angle of 60 degrees, my L cos theta would now be 2000 cos 60, giving me 1000 Newton. So this time 1000 Newton is balancing exactly 1000 Newton of weight. So my aircraft doesn't fall. Okay, so that is the idea here. You fly faster, you have larger lift, then after that you could have a case where it can balance the weight. How does an increase in speed generate increase in lift force? This one is something that you guys learn in SPM or IGCSE, I believe. An aircraft wing generally looks like this. This is what we call an aerofoil shape. So what happens here is that when your aircraft tries to move in this direction, airflow will go in this direction. Okay, so when air goes in the opposite direction and it hits your aerofoil, it will split out like this at the top and it will split out like this at the bottom. So what we'll tell you is that for the airflow below the wings, the speed is less, the pressure is high. But for the airflow above the wings, the speed is high, the pressure is low. So what will actually happen is that there's a difference in pressure causing a net upward force. Something like upthrust that you learned last time. When you learn upthrust, you remember there's a difference in pressure between the top and bottom surface, which in turn causes some sort of resultant upward force, which we know as upthrust. It is something similar for aerofoil also, for wing. So the general idea here was that if your aircraft moves, you would have airflow passing through your aircraft wing. The aircraft wing is specially shaped in this manner, which we call an aerofoil shape. It allows the airflow to move above and below the wing. So what we'll tell you is that the airflow above the wing will tend to move faster than the one below it. So when it moves faster than the one below it, it tends to create an area of low pressure. But for the airflow below the wings, it tends to move slower, so the pressure is generally higher than that of the top. So now between the top and bottom surface, we now actually have a difference in pressure, which in turn cause a difference in force, which is generally outwards. This is our lift force. So when you move faster, you're actually causing the difference in pressure to increase. So the difference in pressure increases, you will have a larger lift force generated. That is the idea behind it. Okay, you're asking me why increase in speed increases lift force, right? It's because it causes an increase in the difference in pressure between the top and bottom wing. So you have increase in force. All right. Okay, so this one is okay. This is for banking of an aircraft. Why does your aircraft need to bank when flying? So I'll just clear this one off. We now move to something that is more relevant that we can see every day. The example we're going through now is for a vehicle rounding a bend on a horizontal road. So this one is something that you can easily appreciate. So if I have a car that was moving in this direction, when it's moving on the road, most roads that you see are not perfectly straight, right? They tend to bend towards the left or towards the right, isn't it? So when you try to follow the road, which bends towards the left or right, it could be that maybe for your current car, you're moving like this, following the curvature of the road. So when you're moving like this, when you're turning towards the left, you're bending towards the left, you are against moving partially in a circle. Okay, so this one is actually part of a circular path. So for this portion, the pink color portion, you're actually moving partially in circular motion. Okay, so for this part, Since you're moving partially in circular motion, you again have centripetal force to consider. It is the thing that allows you to move in a circle in the first place. So now what is actually providing you your centripetal force? Say this one is the center of your circle. What is now providing you your centripetal force to allow you to move in a circle? The thing that allows you to move in a circle right now is actually your sideways frictional force. It is providing you your centripetal force right now. Okay. Now, your sideways frictional force is something like this. This one is your sideways frictional force. Now, in general, it's correct to say this. Now, if I look at the car from the side, this one is say top view. Okay. If I look at the car from the side, this is say the side view. You will be thinking, oh, if my car is moving like this, say this one is my motion, isn't my friction supposed to be in this direction, opposing my motion? Yes, you are correct in saying that. So in the case here, my car is moving forwards. There should by right be friction opposing its motion. But at the same time, there's also a component of the friction that is acting sideways, which is this one. Okay, this sideways friction is actually acting as your centripetal force right now that allows you to move in a circle. Okay, so in this case, it is not lift force, it's not string tension that provided you your centripetal force, it is actually your sideways frictional force. Okay, so if you consider the motion vertically right now, there's no motion vertically, so reaction force is actually equals to the weight. You have vertical equilibrium here, nothing here to consider. But for the case horizontally, you're moving in a circle, your sideways frictional force will be mv squared over r, okay? Because Fc equals to mv squared over r. Fc is provided by your sideways frictional force, okay? So this one is something that you need to know. Now, it's also correct to say Fc is mr omega square, so that Ff is equals to mr omega square. You notice that I keep using mv square over r, right? It's also correct to use mr omega square. Okay, it's just that I don't use this often. I often use this one. Okay, so it's correct to write it in two different forms if you want to. All right. Okay, now one thing to note is this. When your car, just now for the case of the aircraft, I mentioned that when it turns, you ideally want to increase your speed, isn't it? So that you don't fall off from the sky. But now for the case of a car or vehicle on the ground, when you turn, intuitively you don't speed up, right? Because you know what will happen if you speed up too much, right? If you speed up too much, what will happen is that you will lose control of your car, and at the point where you lose control of your car, you will just move off straight, right? So the part where you move off straight is actually you moving at a tangent to the circle. All right. So under what cases do you actually lose control of your car? Under what cases can you not complete a circle? Why is it that usually when we drive and we turn, make a turning, we have to slow down? We know that if we go too fast, we will lose control of the car and then our car will just fly straight off somewhere, right? So why is it like that? Why is it that when we move too fast, we cannot complete a circle? So the statements, the last few statements here will actually explain to you why. Now, you need to first understand this. When your vehicle moves faster, you will actually require a larger centripetal force. Because you can see from here, Fc is equals to mv squared over r. If you try to move faster, your Fc required will also be larger. But here, for the case of a car moving around a bend or moving in a circle right now, your centripetal force is actually provided by your frictional force. And your frictional force has a limit to it. There's a maximum to the centripetal, there's a maximum to the frictional force that is acting as your centripetal force right now, that's providing your centripetal force right now. If it so happens that the centripetal force required exceeds the maximum frictional force available, the vehicle will actually not be able to move in a circle, and you just move off straight along a tangent. So to illustrate to you with some values, let's just say, for example, my max friction is 1000 Newton. And then I move with a speed of, say, 30 meters per second. My centripetal force required is, say, maybe now 800 Newton. So in this case here, my SC is still less than the max friction. You can still move in a circle. Your SC is less, maybe I use a different color, sorry. Here I can say that your SC is still less than your max friction, so you can still move in a circle. All right, so you moving at this speed, your frictional force can still act as your centripetal force. There's enough of it available to act as your centripetal force, so you can still move in a circle. But what if, say, you speed up? Okay, let's just say you speed up. So you speed up too much. What then happens? Your maximum frictional force remains the same. Okay, your maximum frictional force remains the same as before. But now your speed is larger. Say maybe you try to move at 75 meters per second. So now your centripetal force required becomes a lot larger for you to move at that speed. Maybe now it is at 2500 Newton. So you know that your frictional force is the one providing your centripetal force right now, but then right now, the centripetal force required is just too much. Your friction can only provide 1000, but your required centripetal force is 2500. So in your case here, your FC is more than your max friction. So therefore, you cannot move in a circle anymore. Instead, you move off along a straight line tangent, which is this one here. Okay. When your centripetal force requires more than what the friction can provide, you cannot move in a circle anymore. You instead start to move off along a straight line tangent, which is this one. Okay, so this is what you can say. Okay, this one moves off along a straight line tangent. Okay, so that's why we cannot move too fast. If you move too fast, you come to a point that friction cannot provide you your centripetal force anymore. So you start to lose control of your car, and your car will just move straight off and fly off somewhere. Okay, right? So basically, there's one part here. Your frictional force that is acting as your centripetal force has a certain limit to it. There is a certain maximum value to your frictional force that can act as your centripetal force. So in summary, what I mentioned was that if your sideways frictional force was more than or equal to your centripetal force required, you can move in a circle. Then after that, if the converse is happening right now, where your sideways frictional force is less than the centripetal force required, so you cannot move in a circle. So you will actually move in a straight line tangent instead. Okay, so that was one thing to note. So that's why I mentioned to you at that time when your car is actually trying to round a bend like this, you actually want to slow down, because if you speed up, your centripetal force will increase. It will come to a case where maybe your frictional force is actually less than the centripetal force required, so you cannot move in a circle. So for that case, for a car moving in a horizontal circle, you actually want to slow down. It's the complete opposite of that of a plane, where you want the plane to speed up. Okay. Now, so if speeding up when rounding a bend is the problem here, there will be some cases where you really need to speed up when rounding the bend. So how do you overcome this problem? So one of the ways in which people overcome this problem, especially like say race cars, is that if they want to turn at very high speeds, they will actually do it on a bank track. Okay. They won't do it on a horizontal track. They will do it on a bank track, because what will happen here is that when they are trying to turn on a bank track at high speed, we know there's a higher centripetal force requirement there. So in our case, since you have a higher centripetal force requirement, rather than using the sideways frictional force, we instead try to use the normal reaction force acting on the vehicle. Because what we'll tell you is that the normal reaction force acting on the vehicle is actually generally larger than the sideways frictional force. So the reaction force here actually will be much larger than your sideways frictional force. So in turn, it could still provide you a higher centripetal force. It could still meet a higher centripetal force requirement. Okay, that's the reason why we want to use the bank track right now, because we want to use the reaction force right now rather than the sideways frictional force. Okay, so in this case here, when you want to use the reaction force of the car, you can do the simple analysis again. If this view here is your front view or something of the car, all right, what you can see is that you have two main forces: the weight acting downwards, the reaction force acting perpendicular to your track. So this reaction force R is what you're interested in. You want to resolve it into two perpendicular components, R cos theta and then R sine theta. Okay, so let's just assume that there is an angle of theta here. All right, so R cos theta is not really that relevant to us. We don't really want to bother about this, but what we are more interested in is R sine theta. If we assume that the center of the circle is here, this R sine theta actually would act as our centripetal force. Okay, so we are using this component of your reaction force as your centripetal force. So you do the analysis of the forces acting. We know that since the car actually doesn't move up and down, this R cos theta actually is balancing your weight. Okay, right, just now I mentioned that the R cos theta doesn't do anything useful, right? Maybe I was not that accurate in that. The R cos theta is actually balancing your weight. Okay, and then the R sine theta is actually acting as your centripetal force. So these two equations, just take one divide by the other, you're going to get tangent theta equals to V squared over RG. Okay, so this is the last example for a horizontal circle. Okay, then let's just do some example on horizontal circle.